Because my title is important sampling. So I'm going to spend, probably a good bit of time just on this basic overview, maybe upper undergrad level. So I apologize for those of you who are also practitioners, and this will be quite slow. And like I said, in some ways, Ramon wrote down this morning in one line, when I'm going to take pages to describe as an algorithm. So I'm coming at this from a very different viewpoint. I'm also not coming at this as someone who does research on sort of generic particle filtering methods. So I do some sort of specific research that if I have time, I'll get to at the end on using particle filters and data assimilation methods on Lagrangian data assimilation. But after I talk about Monte Carlo and importance sampling, the algorithm for particle filtering is so, the sort of the correct algorithm is so natural that you don't even realize you're using importance sampling. Right, so I sort of want to mention where that comes in. In that discussion, I'm just going to apologize now for my abuses of probability notation, sort of taking the engineering stat methods notation. Also should apologize. I think I got my notation straight, at least consistent with itself, but then I put in a bunch of figures that I told from another talk that have different notation, but they're color-coded, so you can look at that. And basically, for references, these are just general sort of simulation books that talk about importance sampling and other various reduction techniques, the first two. The third one is importance sampling for rare events specifically. And for particle filters, so there's the book by Doucet, and Doucet's website has lots and lots and lots of references of all sorts of applications and such. And this is sort of a paper that I see come up a lot sort of in the user community that has sort of, it's not quite a review paper, but it has sort of a nice review of some of the development of particle filters in the engineering community in the 90s. And like I said, at the end, if I have time, I'll get to one, maybe two examples of using particle filters with importance sampling in Lagrangian data assimilation problems. Okay, so very generic. I have random variables. I have some function g that I'm interested in. And I'm going to describe cap g as just being the sampling mean of that with n samples. Right, I take this expectation, of course. The expectation of cap g is going to be the same as the expectation of little g. And the variance of cap g of my estimator is just going to be 1 over n times the variance of little g. So if the variance of little g is finite, then this thing converges. Right, that's something I'm sure we all know. And this is sort of the standard Monte Carlo approach. I'm always just thinking about Monte Carlo as an integral. Right, so I have the expectation of this random variable g with respect to f. So I'm just integrating g against f. And I'm going to get the same answer if I look at the expectation of my estimator versus the expectation of this random variable that I'm interested in. So, and here's the idea. So here's Monte Carlo. Basically, I'm going to approximate this integral by taking samples from the distribution f, plugging them into g, and then averaging them. Right? That is Monte Carlo, and that also is exactly basically my estimator up here. So this estimator is really giving me an approximation to the solution. The other case I was sort of interested in is when you're in the tail maybe of the distribution and your g is 1, but you apply this same technique. So this is just going to give you an indicator function past some number, 30, 50, whatever you're interested in, that your random variable lands over there. And this is also true, and it also converges. But of course, in practice, you would never actually get samples over there if A was large. Right? So these are the sorts of things we're concerned with. And of course, as was mentioned, if you take enough samples and the things you're trying to estimate are finite, it will always converge. But in practice, that's very different than sort of how much is enough to converge, or how much is enough to have some sort of reasonable answer to talk about. right? So the way we think about this is about how much is enough is looking at Chebyshev's inequality, right? So here I have the difference between my estimator and this integral I want to calculate, and basically the probability that that difference is going to be bigger than, is going to be big, right? Bigger than you'd like, you want that to be small, right? That's all Chebyshev's inequality says. Right, so you don't want your estimator and your exact solution to vary more than that. And it's going to vary more than that only with probability delta. Right, and so basically, this variance of g over delta n, this is what we're thinking of as our error between our estimator and the integral we want to estimate. And so delta is fixed. You've decided you have some tolerance on the probability that you're going to be wrong. So basically, this is sort of the key to Monte Carlo, or the key to importance sampling, is you can either change n or you can change the variance of g. Those are the options you have. So changing n, right, of course, is just more n. So you're going to think about how do we change the variance of g. And you want to decrease it, right? So importance sampling is one of many methods that fall in this category of variance reduction techniques. But again, we just want to think about going back to sort of a generic integral. So I have this 1D integral, and I can choose how I'm going to break it up into a product of two functions, and one of those functions is going to be a probability density that I'm going to sample from. Right, so say I want to integrate x cubed. Of course, there's no reason to do this, right, with Monte Carlo. But say this is what we want to do, and we want an estimate of this integral accurate with an error of within an error of 0.1 and a probability that our estimator might exceed that error by 0.01. Right, so to do this, we have to break up x cubed, like I've said, and we're just going to, so f, of course, is going to need to be positive, and its integral is going to have to be 1, so it's going to have to be normalized. So you can think about, right, you could just think about any way you'd like to break this up and play the game. Right, so I guess when I talk about this kind of problem in a simulation class, I mean, of course, there's two reasons you might want to break something up. Because it's going to help you out with your variance reduction, or because it's easy to sample from, right? Those are the two motivations. So here, we can choose f to be uniform. That's easy to sample from. And it just have to normalize it. Or we could choose our distribution, what we're drawing samples from, to be the normalized quadratic. And then this leaves us with the function that we're integrating against. Or that we're integrating against f. Right, so all of these just end up being the integral of x cubed. The key is with those two different choices, I have a factor of 20 difference in the number of samples I need to take just from having two different choices. Right, so why is this happening? And basically, we need to calculate the variance of g. And really, a picture like this is going to sort of tell you why this is happening in some sense. Right, so here I'm sampling these little red dashes are just samples from the uniform. And here they're samples from this quadratic. And I think all Monte Carlo integral is doing is right there where I have a sample, I plug in. And then everywhere I have a sample, I plug in and I take the average. Right, that's all Monte Carlo is doing. And so with the uniform, I'm plugging in a whole bunch down here that aren't contributing to my integral. But over here, where I have a function that where I have a distribution that kind of looks more like my integrand, I put more samples where my integrand is big, and this difference is a factor of 20 less to get the same error in your estimator. Right? This is the sort of motivation for why you'd want to pick an importance distribution. Right? You can think about actually calculating these variances is telling us sort of how good we're doing, how much we're improving. Right, so again, our error between our estimator and the integral we want to calculate is just this. Right, it's not a good way to do integrals, and in 1, maybe 2 dimensions generally, because of course it would look worse than the first integration method you learn in Calc 1. But that's okay if it were on a grid. And you know, if you choose a bad F, maybe you get something that's hard to sample if you choose a bad importance distribution or just distribution to sample from. Right, and then the pros, and this was talked about, right? So the error is independent of dimension. And this is, you know, the key for importance sampling is we have some freedom to reduce this variance, right? And of course, sometimes these integrals just come to us in a stochastic problem already in this framework. So Monte Carlo is natural.
But the end depends upon which function you choose, right? Between that 3/8 x squared, 3/8 x cubed, and uniform, right?
How many n I need to use?
That depends upon the kind of function.
It will, yes, it does depend on the function you're integrating in some sense, because you're interested in.
Between the functions, one was uniform and one was
Right.
3/8, one was cubic.
Mm-hmm.
And the number of n you choose to meet the error will depend upon that.
Yes, the number of n that we need to meet the error.
Divergence rate is independent of the type of function.
It's not independent of the type of function I choose. I mean, that's happening because this function looks more like the function we're trying to integrate.
Okay, but even then the order of 1 was 5 root of 10.
Everything's 1 over square root of n.
Okay, but the constant is going to depend upon the type of function.
The constant depends on the type of function you choose. Right.
The type of function, but also the underlying distribution.
Yeah.
So it's all combined in one thing.
Right.
G of x. So she had the choice of choosing G as well as x and so on. So that's what she's talking about.
So basically,
1 over square root of n will be there. That's what is being multiplied by this constant variance for the standard deviation of G of x. And so that's what she has to control.
I think it will come up more as I go, that idea. So, right, so the idea though is we can break this up. We could break up this integral however we like, right? So even if it's given to us as sort of some probability, as sort of some expectation, we can break this up however we like. And the idea there is to choose some, what we call an importance distribution. So that I'm labeling F tilde here. And just multiplying by 1, right, by the importance distribution over itself. So now I'm going to sample this guy F tilde. I'm going to sample F tilde, and now this is the rest of what I plug into for my estimator there, right? So I sort of have a G tilde that is the rest of my integrand. And now I can think about, instead of doing Monte Carlo sampling from F, what if we sample from this F tilde? Right, so I want to pick some other distribution. So now my Monte Carlo error is determined by just the variance of this, what's left over here, which is just some other function. Right, so that was exactly what we were trying to reduce before. So we're trying to now reduce the variance of G tilde, and the expectation with respect to the distribution F tilde of G tilde is the same as the expectation of the distribution with respect to the distribution F of G, right? All I did here was multiply by 1. I didn't change the problem. Okay, so we'd like to minimize this guy. And basically, it's just a little variational calculus problem. We'd like to minimize this piece we have control. This other piece is a constant. Subject to this F tilde being a probability distribution, right? Being positive and its integral being 1. This is just a little Lagrange multiplier problem. And this is the solution to that Lagrange multiplier problem. It says F tilde is going to be proportional to G times F. Right, so there's sort of two questions. Is this a reasonable result and is it a useful result? Right, and those are different things. Is it reasonable It is, because if we choose this, we get a variance of 0. That means one sample and my estimator is correct. But it's not reasonable, really, because if I were to normalize this choice of f, that's exactly the problem I was starting with. Right? So my solution is the problem I'm trying to solve. So in that sense, it's not reasonable. Is it useful? And this is sort of, I think, the motivation that should be the sort of motivation behind using any importance sampling for the mass of a distribution, for the tail, is does this f tilde you chose, does it look like the integrand of this integral you're doing? That's what you want, right? So this is just the integrand of the integral you're doing. You want to choose a distribution that looks like that, whatever that means. So that's really the idea to take away about importance sampling. That's the goal. Finding such things is non-trivial, for sure, especially in high dimensions. But we'll look at just a couple examples here. So here's an example. I mentioned how we're sometimes when we're interested in the mass of a distribution, or in the mass of a function, here just integrating this blue function. And sometimes we're interested in the tail. So here's a mass example. So this would have been a good sampling distribution, right? It's big where the integrand is big. It's smaller where the integrand is smaller. It puts lots of samples in the middle. We're taking, basically just taking the averages of the red guys. This would be a bad distribution. And here, let me go back for a second. Right, this will come up again in a second, but f over f tilde is something we call the likelihood ratio. And that's effectively what we're plotting here. And these numbers are pretty reasonable. Over here, where we have this clearly bad distribution, right? Our importance distribution doesn't look like the function we're trying to integrate, and we get these huge numbers when we look at this likelihood ratio. And you can also sort of see the variance being different too, because really the variance we're looking at is the variance in y of those red dots, right? That's much less for this estimator than it is for this one, right? And that's the variance we're trying to reduce effectively. So one of the problems, I see this as a problem from a practical point of view, is if the thing you're trying to sample with importance sampling converges, even though this is a terrible importance distribution, you take n to infinity and it still converges. You're still eventually going to sample over there and get the integral. Okay, so here's just another sort of toy example. So I want to integrate cosine. If we take a uniform distribution for our importance distribution, this is now our error, right? This is that variance calculation is about 0.09. And so really what we want is to pick something that looks like cosine. So again, this is the moral of the story. How can I, what tools do I have at hand in the problem I'm interested in to try to get importance distribution that looks like my integrand? Right, so the tool we have here is just a Taylor expansion. This guy hits 0 before 1, so that's not going to work. So we'll just take the Taylor expansion that looks like that hits 0 exactly at 1. Right, then you need to normalize this. But now if you do this variance calculation, right, we've reduced that variance by a factor of 100. Right, we've reduced the variance by a factor of 100 just by thinking about the problem a little bit before going forward, basically. Okay. Right, and this is how it shows up in the Monte Carlo then, right? So this is our original goal. That's still the thing we're estimating, right? Because these two expectations are the same. But now, what do we do in practice? In practice, we're sampling from f tilde, right? These xn's are now coming from this importance distribution, and I have to now not just plug into G, but plug those samples into the likelihood ratio. And the likelihood ratio really tells you how likely would the sample that I got from my importance distribution, how likely would that have been if I had gotten it from the actual distribution sitting in my problem? Right? That's effectively what it's telling you. And so this will always then, if you're doing importance sampling, this will pop up in your Monte Carlo. Right? So you're still sampling something which sort of disappears from the equation, right? Because you're sampling it. So you're sampling from F tilde, but this likelihood ratio then appears in your Monte Carlo. And this just to let you know that if your random variables are independent, then the likelihood ratio of a bunch of independent random variables is just the product of likelihood ratios. Pretty straightforward. Okay, and then here is the tail sort of problem. So again, I'm interested in maybe the probability that my random variable is very far away from the mean or from some value of interest. And right, we can write down the Monte Carlo. It's guaranteed to converge, but in practice, it won't converge. You won't get samples over there if you just do the standard Monte Carlo, draw from your distribution. Right, the indicator function is just, did you get past A? Right, that's all you're asking with the samples that you're drawing. But none of the samples get past A if A is far away from the mean or something. This is completely arbitrary, but rare event is maybe what you want it to be, but something with a small probability typically. And if we want to do this with importance sampling, right? So again, it's the same function we had here, just this indicator function. But now we're going to sample from some importance distribution, some bias distribution, and correct for the fact that we've sampled. Right? And that shows up just like it did in the generic case back here. Okay, with our samples now coming from this importance distribution. So this is a very cute little example. So you want to flip 100 coins and see what the probability of getting heads 70 more times is. We could probably all write down the binomial that would give us this answer. It's, it's 2 to the negative 13. And the trick is, right, I mean, if you do this to the negative 13, you flip 100 coins, you keep flipping 100 coins for the rest of your life, you're never going to see more than 70 heads, right? 2 to the minus 13. It's just maybe once, but then you can't get statistics on it. I mean, you could get real lucky and you still can't get statistics on it. So the idea then is to use a weighted coin, right? And if you know something about your distribution, so here we know we're interested in finding sort of what falls right around 70, because that's going to be the mass of that integral. Well, then I'm going to use a coin that's weighted to give me heads 70% of the time and tails 70% of the time. Now, instead of basically tailing ones that my objective of getting 70 or more happened or not, I'm tailing likelihood ratios, right? Because I have to account for the fact that I'm using this biased coin, and the way I do this is take the probability of the fair coin to the probability of the biased coin for the event that happened, right? And you do a simulation like this, and it's 10 orders of magnitude. Of course, the hard part is picking this correctly. And often in low-dimensional problems, you can maybe sort of force your way over there. In high-dimensional problems, that's really you really have to use something. You really sort of have to use somehow from somewhere in the problem some knowledge of the state space. Where in the state space really is sort of giving me this probable rare event that I want to target my sampling at. And that's definitely something tricky. So here's another example of just a rare event. So I just want to find the probability of a normal random variable being bigger than 4.5. So that's way out here, right? And so then this is just sort of the difference between targeting mass events and tail events. I don't want to sample from a normal, right? Even though that looks, I mean, my integrand right, was the integral of a normal distribution, but that's not what I want with a tail event. I want something that looks like my tail, right? I want something that puts a whole bunch of mass up against that indicator line. Right, so for an importance distribution, you could pick something like an exponential that's shifted over, and then calculate this probability with no problem. Right, this is just sort of the tricks of the two methods for importance sampling. Okay, so again, the reason I wanted to, well, beyond it being just assigned me as my title for the talk, the reason I wanted to talk about importance sampling was to describe where it comes up in just a generic particle filter. And then if I have time, I don't know how long I go to. Half an hour. So maybe I'll have time to get through to one example of a project actually Amit and I are working on that uses importance sampling in the context of Lagrangian data assimilation. Okay, so this is, we've seen this many, many times now. And again, I already apologize for my notation. I have some background distribution. I'm just putting on F's for forecast for prior and A's for analysis for posterior, just to reemphasize that it's the same thing, right? Data assimilation and particle filter are really one and the same. So I have some background distribution. I have my model that moves me forward. Associated with my model is some transition density. We have some observation operators given to us and observations and some function or some distribution describing the model noise. And of course, to get from x naught to distribution from x naught to x1, so I have some probability of being at x naught, and I want to, and some probability of transitioning from x naught to x1, and I want to integrate that over any possible x naught. And I do that, I get the probability, my forecast probability x1. Right, so here is sort of Bayes' rule written down sequentially, and we're thinking about then sort of collecting things over time. So we have our forecast, which is just using the Markov property. So we keep multiplying by the probability of transitioning. And I should say, right, this in this case, and when we use it at subsequent observations, this is the integral that's hard if the model's nonlinear, right? This is why we have discrete algorithms to do this, because this is hard to do. So I have the prior. I have my likelihood, which is just going to be the product of all the likelihoods if the noise is independent on the observations, and then I have Bayes' theorem written down. And really in here, can think about, there are really a whole lot of integrals buried in this normalization, even though I've just written one symbol. And then if I want to marginalize this over all the previous time, so my time here is counting in j up to n, over all previous times, then there's even more integrals sitting in this normalization, right? And that's kind of, this normalization is kind of the key to why the algorithm looks like it looks. So one step in the most sort of generic particle filter, so I transition, I have my prior on time 0 and 1. I can find that for time 1 by doing this integral. Effectively, what we're doing this integral now is we're going to sample from this prior distribution on the initial conditions, move each of those forward through the model, and then have samples of this prior distribution at time 1. Right then, we have our formula for Bayes' rules, right? So here's where we're gonna plug into this algorithm. So we're thinking about a particle as a weight being attached to a state. For the x1 case, it's equivalent, but for future cases, I agree, you need to be more careful. So here's how we would do sampling on that version. So again, I'm going to think about a particle as a state value and a weight. I have n particles. So I sample from my distribution of initial conditions. I set my states equal to those samples. I push this forward. I push each of those states forward through my model, right? So this is Navier-Stokes or whatever your model happens to be. Now at time 1, I have an approximation to the prior distribution, which is just those states pushed forward, and those states initially were sampled empirically, so they all have even weights. And the key here, right, and really what we're doing is now we've sampled from this PF of x1, right, which was just this guy. So we've sampled this distribution, right? So to avoid having to calculate this integral, we're just sampling it. Right, the algorithm is actually sort of doing the sampling for us then. And so we have samples of this prior distribution of x1. And effectively now all I need to do is weight my samples by the likelihood of having seen this first observation and normalize. So now this is going to give us our posterior distribution. So we've already moved them forward, so those states stay the same. All we're changing is the weights. Right? So all that changes with this update step is the weights. The states themselves there are fixed. And again, the sort of key here is the normalizing integral for so sort of why this doesn't work going forward, this process. So Monte Carlo simulation, right? So maybe we want to, this whole distribution on all of the states at all times are just marginalized. But over all of our observations, right? So again, it's just this algorithm I described. So we take our samples at time 0, move them forward to time 1, evaluate the likelihood between the state and the samples, and we just keep pushing it forward and keep evaluating likelihoods. By the time we get maybe 2, 3, 4 samples, numerically things break down. Numerically things break down, if we go back, because of this integral. Because we've sampled from this original distribution empirically, and effectively what we're doing here is evaluating however many steps we've taken a whole bunch of likelihoods. And so what tends to happen is you can imagine these likelihoods might be small, and you're taking products of small numbers. So maybe you have a few that are big, say maybe 2 of 100, and the rest of them are really quite small. The problem with this integral numerically is that you've sampled empirically, so your weights here are 1 over n, right? And that makes this normalizing. That's saying, well, my average of this thing should be maybe these couple sort of substantial weights and a whole bunch of small ones, and that's going to sort of kill the numerical stability of this. So the idea, which you know is sort of always what you would just describe as a particle filter anyway, is to not sample this empirically, but to use your prior distribution at the time, given all the previous observations, to use that as your importance distribution effectively, right? So that's the idea, and the idea there basically, then we can, I'm hand waving a bit, but basically we can think of this now is that and effectively what that amounts to is normalizing every time. Right? You normalize this every time you update, which is what you do in practice, which the algorithm tells you to do. And then when you normalize every time, you're sampling now instead of empirically, you're sampling from your analysis distribution that pulled forward. So now it's the forecast distribution at your next time, and those are particles with weights. And if the weights are high, likely the new observation, if your weights were high, it was pretty probable to be there as a prior. Hopefully that's close to your observation. And then this weight will be pretty high, and this integral becomes numerically stable. Right? So this is why we sort of need to normalize after every step. You know, there's no other reason to do it. It's equivalent with n going to infinity particles. But it will break down in just a few steps if you don't do that. All right, so here's the algorithm to do what I just described. So you normalize every step and treat the posterior distribution as an important distribution for the next step. Right? So again, we start where we started. We transition each of the particles forward according to the model. We evaluate the likelihood. And it's always going to look like this now. So the weight of the particle from the previous time step times the likelihood, and we normalize it. Right? And then we just repeat this process, and this is kind of the key, right? Then at step 2, I've moved my model forward. So I've moved each of the states from time 1 forward in the differential equation, partial differential equation, to time 2. They've, for forecast, they've held on to their weights from the previous step. Right? So now this is effectively our importance distribution, which is completely natural. I mean, it's completely sort of how you think about data assimilation anyway. And then you just update your weights, and you keep going. Right? You keep doing this. So this algorithm is called sequential importance sampling. And it can work pretty well if the dimension is small, and especially if you have a deterministic model. You still have issues, though. You can still sort of have issues with your weights where all of the weight collapses onto a few particles. And there are in various problems and much more sophisticated ways to try to address this. Some more ad hoc than others. But the basic solution is resampling or bootstrapping. So basically, this is what you want to do. So you just want to sort of proceed as long as you were, and you want to monitor your weights somehow. So you can calculate an effective weight. There's sort of formulas for that. You can just say, oh, I have some, if too many of my particles have too small weight, then trigger resampling. And then we want to bootstrap from our posterior, sort of when we see that this is triggered, that our weights are getting too concentrated. And when we do this bootstrap, the key is now I want to sample from this distribution empirically. So I'm sort of treating this as an importance distribution. And when I sample something empirically, that means I set all of the weights just to be even. Is there anyone who's not familiar with just the idea of a bootstrap? Everyone's familiar with it? Okay, I won't talk about it more. So then our weights are set even, and we transition forward, repeating as we go. Right. So this is a sequential this algorithm is sequential importance resampling. Generically, when you hear these other words, I mean, and I'm talking sort of in the user community of particle filter, bootstrap filter, sequential Monte Carlo, this is the algorithm. This is sort of the generic algorithm people are talking about. This algorithm. And with the bootstrapping, if your model's deterministic, you need, this is sort of generic bootstrapping, you need to do something a little fancier, somehow to search around your states. Otherwise, you'd sort of have multiple copies of states that were quite likely from your bootstrap. Okay, so now I want to apologize a little bit. I'm going to, I have some sort of pictures for the algorithm, but they're taken from another talk. Mm-hmm. Because the resampling doesn't get around the problem, the sequential importance sampling gets around it. Right. So sequential importance sampling gets around the normalizing problem that you really need to normalize on every step. The resampling is trying to address the fact that even if you do that, your weights might collapse. Right, so they're both sort of importance sampling and used in very subtle and natural ways, right? So you might not even realize you were using importance sampling. It just seems like sort of the way to do things. Okay, so now I really do want to apologize because I've just stolen a picture, sort of cartoon of particle filter from another talk that has really different notation. So I apologize for that. Just sort of ignore the notation. But things are color-coded, so we can just sort of see a picture of the algorithm. So right in the data assimilation framework, and this is a slide stolen from Chris Jones. Probably many of you recognize it, or at least this picture. Right, so our model pushes forward. We have an observation. We assimilate, filter, whatever you want to call it. There's some update done there. Right, the particle filter, we're updating the weights in a Kalman filter, ensemble Kalman filter, we might be shifting the states, right? It's just sort of different approaches. Then I have some posterior distribution basically sitting here. I move that forward from in the model. That becomes a prior distribution at the next step. We repeat the process. So here I'm just, so you can sort of forget about the details of the notation since it's different from my derivation. But you can think about color-coded. So red is going to be posterior samples. Blue are prior samples. Right? And our Monte Carlo step is effectively the transitioning of the cloud. Right? So these are the same clouds that Dan had on his picture. Right? You have these same little clouds that are going by. And again, each particle is a state and a weight associated with it. So if I had sort of colored these according to weight, it'd probably be a little darker in the center and lighter on the outside or something. All right, so here we have our prior distribution. Basically, a particle filter is just applying Bayes' rule to every particle discretely. So here's our observation. So we compare each of our particles from the prior distribution at this next time step to the observation. That's going to re-weight our particles. And so now we have a posterior distribution that's here. And here the color coding is it's just really sort of picking up the high weight problems, right? But until I do resampling, all of these are still part of this posterior distributions. But only the red ones, the ones that sort of had a high weight coming from the likelihood update are sort of contributing to the mass of that importance distribution. All right, so here's the cartoon. And right when this cloud it becomes too tight, there's too much mass on just a few particles, then we do some kind of resampling. So this is basically the Bootstrap algorithm I described. So you can just think about, I can think about just taking copies of this posterior distribution at this time step proportional to the weight. So this one that has the highest weight, he has 15 copies, and these guys have 7 or 8 copies and down on. And some of them will have no copies, right? And that's exactly what Dan was referring to when the algorithm is just going to cull particles, right? So if you have particles without any weight in this resampling step, they're going to be culled, right? So then we do Bootstrap then effectively here. Like I said, if your model is deterministic, you have to do something to sort of spread these out because 15 copies of the same thing doesn't do you any good. But if it's stochastic, then that's kind of fine. Okay, so this is just sort of the generic particle filter. Any questions before I go on to talking about Lagrangian data assimilation? All right, yeah. Mm-hmm.
Particle spreads out naturally.
Right.
So parameters, what do you do then? You have to do something to them.
Right.
You never know what exactly.
Right. I don't know. Are you going to talk about that a little bit, Nara?
Yeah. I mean, how do you call this? Use artificial random form, form,
I mean, yeah, there are a lot of flavors to do that, but I can't say that there's one I would prescribe to for parameter estimation. But yeah, that is a concern, definitely. All right, so Lagrangian data assimilation. So we're thinking about taking observation from instruments that live in the ocean. So there are sort of three generic kinds: floats, drifters, and gliders. So I don't have gliders up here because floats and drifters are sort of purely Lagrangian. They're just passively moving in the ocean. Drifters are basically on the surface, just dredged right below the surface. And floats go down about 1,000, 2,000 meters to some parking depth and have a Lagrangian path down there, and then they come up. Right, so that's, these are instruments. So you're going to get so you get positions of the drifters from GPS. You don't get position of the drifters for the floats in between surfacings. Right, so you have this. So this is some other work that Ahmed and I have worked on is sort of how do you deal with that fact that you have this Lagrangian path subsurface, that you have, your data is actually, any sort of prognostic data is being collected on this Lagrangian path, but you don't know what that path is. You just know the endpoints of the path where you've surfaced. I'm not going to talk about that today. Right, so and then, you know, we're going to have some model for our velocity field. I mean, this might be a ROMS model, a global model, or it might be something very local to something coastal. Right, and this of course is going to be coupled to things like temperature and salinity typically. And we have a model for the drifters, but these drifters are just advecting passively in this model, drifters and floats. Right, so we're interested in maybe some of these prognostic variables, and also the position of the drifters and floats. So here's just a spaghetti plot of drifters, right, to sort of get a sense of what this data might look like. Right, so Chris and Kaio, Ide, and Lena Kuznetsov, and Haider Salman really did a lot of the work on framing what I guess us of us who work in it now call Lagrangian data assimilation. And basically, the idea is to append the drifter coordinates to whatever your state is, to your velocity field, effectively. So any sort of prognostic variables and velocity field are going to be collected in this this XF, where I'm thinking about flow, and the position of the drifters are going to be collected in a variable called XD, right? So that's just going to be two-dimensional. I've heard there is one guy, I don't remember his name, I think he's in Seattle, who actually has three-dimensional floats that he develops and plays with, which is really cool. But Z is very tricky in the ocean, so most people avoid that. All right, so now if our state is a combination of these two, we have this sort of skew product structure, right, where our state evolves forward according to our model, and this model has this velocity component and drifter component, which are coupled one way, of course, right? So the flow doesn't care if there's a drifter in the flow or not, but the drifter, of course, depends on where it's at and what the flow is doing where it's at, right? So, and we're just thinking about, generally thinking about this model as being our velocity field, right? And here's the reference I already gave to those people who sort of pioneered this field over the last decade or so. And our observation operator is now just going to be projected onto those two variables. So it's linear, it's just going to be the identity, but in a very small subspace of the problem. Right, so it's linear, but these observations sort of inherently, right, because of where the drifters ended up, include information about the flow. And both Leonid and Haider have papers where they've implemented some form of ensemble Kalman filtering, extended Kalman filtering on these kinds of problems, and it can work if the observation period's not too big. But even if the model is, and I think Amit's going to talk about this more, even if our velocity model is, yeah. Yes. The model's deterministic, but these drifter paths are going to be chaotic, typically. Yes. Well, no. So either linear or nonlinear.
Why did you assume particular? Go back to the last slide. Because I could have had the y as the drifter. I would have a stochastic or differential stochastic differential equation. dy by dt is equal to the vector field plus the noise.
Sure.
If we're not augmented, we have a dynamic observation.
I would say the reason to augment it more than that, I mean, I don't think that's, I mean, that seems to more be trying to account for the paths being tricky, that kind of approach, which is a reasonable thing to do. The reason to augment it is that typically the flow variables are going to be on a grid, and our observations are not going to be on that grid. So our observations are Lagrangian. They're not going to show up at the grid points of our PDE. And so if we don't depend them, then we're going to have to do some sort of interpolation of our data, which is going to end up having a nonlinear observation operator. And some
Actually, if the observations are not, next slide you mentioned that, so the observations are not continuous in time, then the observations are not locally dependent on X. But everything is continuous. So then I guess, yeah. So I think
Oh.
formulation, they are done at dy.
no, no, they're not continuous. This isn't a process. This is at one time.
Go back to the okay. This is what your dxt is the flow, right? This is the drifter. And that is the information that you're collecting. And that flow is driven by the flow.
Right.
And then if you add a noise to this, that would be like a y.
yeah. So if you work in the continuous time observation case, then both of these are possible.
Right.
Augmented or non-augmented. Discrete in time.
Oh, okay. You got to make discrete now.
Yeah, it's discrete in time. Yeah.
The observations which are discrete.
And the observations, if from floats, are inherently discrete in time, right? They go down for 8 to 10 days and they come up. Yeah.
Is the period between consecutive observations random?
No, so 8 to 10 days is what you hear for typical in the ocean. I actually don't know exactly how they're programmed. Do you?
It's variable, not random. You know what it will be. You know what the time is.
Deterministic.
Yeah. So the delta comes up and it tells the satellite what time it's transmitting the data. So you know the data, but the time could change. So
Yeah, I mean.
it's not that it's equidistant.
Right.
But you know the time.
You have time dependence in the model, in the evolution of the model.
No.
Because you discretize according to when you observe, you get the observations. So it just takes longer between two observations. If it takes shorter, then you move.
Yeah, I mean, there could be time dependence in the model, and why not?
So there could be, but
Yeah.
I don't think the variable time dependence, the variability in the observation period needs to imply that the model is, so the model is what it is. Right? I'm just collecting the data at various times.
Yeah.
And at what time I collect the data,
There's a fundamental difference between collecting data at discrete and fixed times and collecting data at random or variable times.
They're-
no,
they're-
exactly, that's what I said.
They
So
are,
we are not collecting data at random times.
they're close to discrete. Of course, it's not
We are
perfect.
collecting data at discrete times.
Yeah.
Which are not spaced temporally, but we know the spacing.
Okay. But then you
It's
have
not
to
random
adapt the evolution
What percent of
of
flow?
the state according to those.
Doesn't the flow collect the data continuously? Every time? No. So it comes out only discrete. Or it's collecting data.
So it can collect, I mean,
So if it does,
I mean, it's underneath it, it's collecting data, it comes out every 12 hours or 13 hours every day.
mhm.
That's true, but it's collecting the data.
So so it is collecting data, or they can collect data. No, that's really not what it's used for, though. So it's really used for the profile to come up. So effectively, you can think of it as the way oceanographers tend to use this is they have information, very good information about the column where this thing rises for floats. And so there is information collected along the path, or there can be, it depends on if they program it to do so. It's typically less frequent, so it's going to be very frequent on the ascent, but typically less frequent and often not really used, maybe just averaged. And part of the reason it's not used is because it's Lagrangian, but they don't know where the path was. They sort of don't know exactly what to do with the data. Yeah.
Just a comment on this line.
Yep.
We used to do assimilation of continuous observation
Your observation affects the model. If you don't have that in your model,
No, the observation doesn't affect the model. I mean,
time you think, because you have variable time between observations, it should affect the model.
but I mean, you integrate up to the time that it comes up. I mean, if you're just integrating the drifter, yeah, so it affects, yeah, I mean, that's what the model for the drifter is. It's just integrating the velocity field up to whenever the time is that it comes up.
Right.
Yep. So that's this piece.
Right, so the discretized version of that is not as time homogeneous partial chain.
Okay. All right, yeah, 2 minutes? Okay, so anyway, basically, the limitation that was found when people did studies on this kind of setup with ensemble common filter was the period between observations, because the paths of the drifters or floats can become chaotic effectively. So you.
So this period there means the interval between two
And-
consecutive observations.
Yes.
The period of collective observations.
Right, no, the period between 2 consecutive observations, right. So Amit and I are working with a grad student, Laura Slavinsky at Brown and her advisor Bjorn Sandsteed on developing a hybrid particle filter ensemble common filter that basically, and the motivation behind this is the drifter equation. This might be quite nonlinear. This will be quite nonlinear typically, but it's always low dimensional. It's always 2 dimensions. And this, if it's a PDE on a grid, this is high dimensional. This is going to be expensive, effectively. So that's the motivation here to think about effectively decomposing this space where we have here just 4 flow variables in this cartoon. Right, so we have 4 different copies of our velocity field. And each of those, instead of 1 drifter, which is what an ensemble common filter would have, we're going to have m copies of the drifter coordinate. So so we can think about this as I mean, it is just a particle filter effectively where the particles are much denser in some dimensions than in others, which is in some ways just natural to this problem, because that's where it's nonlinear and it's low dimensional, so that's where we'd like to really sample. And basically, between resampling steps, we just treat this as a particle filter. We treat this as a particle filter, and that's fine, but again, once we need, so this is here, once we need resampling, we sort of have a 2-step process. So we resample the drifter coordinates. So every drifter lives in one of the copies of the flow, so subject to the flow it's in. But we resample the drifter coordinates according to that posterior distribution using the observation. But that's not what we do with the flow members. So with the flow members, instead, we don't change the weights. They're going to hold on to their weights from the previous step, but we change the location of the states based on an ensemble common filter update. So we do an ensemble common filter update for the location of the flow variable, location in state space. I mean, for sort of moving these particles around, and just a regular particle filter on the drifters. Right, so now we have this sort of weighted ensemble, this weighted hybrid filter, effectively. Right, and this is, again, sort of what it's capturing. So here, this is a if the truth, so the truth in, you know, in spirit should be a sort of a draw from this distribution, loosely used term distribution of paths here. So, but this drifter, we're in this chaotic system where it could have meandered down here. You can see lots of paths going down that way. And this case wouldn't have sampled that at all. Right? And this is the motivation to sort of expand your search in the dimension where things are very nonlinear. Otherwise, use the technique that sort of people know and like to use in high dimensional problems. Right? So that's the motivation. So something Amit and I have been talking about just recently, I should say Laura did some work to show that if the flow, if actually your model for the velocity field is linear, then this gives you the correct statistics in the linear Gaussian case. So you can just sort of grind through that calculation, and this representation of the analysis gives you the correct distribution with the old weight. So we were trying to think, well, what should we do if our prior distribution, if it's come from something that's not linear, and so maybe now we're in this case where we don't have a normal prior. Right, so here's just a 1D sort of cartoon we've been thinking through to deal with this. So here I have samples from a prior distribution, either empirical from this or from some other distribution and weighted to be samples from this. It's equivalent. And then I have an observation at 3/2 that's Gaussian. And they have the same variance. So we end up, if we, right, so the common filter, if we were just doing a common filter on this, effectively this simple problem we've set up would just be averaging random variables from the green and blue distribution. The distribution of summed random variables is just going to be the convolution of those two distributions. The convolution of the green and the blue here is this red distribution. So that's what the ensemble, so a common filter, ensemble common filter, whatever, should give you. This is actually what the posterior distribution looks like in this simple case. Right, so we have this sort of skewed posterior distribution in black, just from one step of a particle filter Bayes theorem, say, tons and tons of particles, so it's smooth. And if you actually go ahead and do the common filter, sort of do the approach where you shift according to the common filter but hold on to your old weights, you get exactly what the common filter should give you, theoretically. And now we sort of have two strategies. So I'm thinking about if I have an A here, that means I had a common filter update, and old weights or new weights are just if I've updated them with an observation. So basically, you're thinking through sort of two ways to try to better target the posterior distribution, still somehow using a flavor of a common filter. So one way we were thinking of is to go ahead and change the weights and try to sample from, we want to sample from, so we've changed the weights, we'd like to sample, so here the posterior, I'm thinking of what would, if I did the particle filter on the next step, what would mean and variance would I get out of that? Right, so this is my target distribution. This is actually the distribution I sampled from. The common, my common shift is effectively sampling from this distribution. So I sampled from one, this is my likelihood ratio, this is the update for the weight. If we do this, and this is actually an algorithm that someone, I'm sorry I'm forgetting the name, and I think the paper came out in 2010 called a hybrid particle filter, but they only mean sort of in this case of adjusting the weights in this manner, as far as I understand the paper. So, so if we do this, we get this cyan curve, right? So I've shifted my states, and they were attached to this old weight, but now I've used importance sampling to try to get the mean and variance of the actual posterior distribution. And this cyan, it's still a Gaussian, but it has the mean, and so this cyan curve has the mean and variance of the black. Right, so that was sort of the goal, to get to figure out how could we do a bit better. Another approach is sort of to do the opposite, to leave to not shift the particles according to the common filter, but just so as we're sampling from the prior distribution, right? So here's our prior distribution we've sampled from, or not the, this is actually an approximation to our prior distribution, so a Gaussian approximation to it. And, right, which is sort of corrected to be our prior distribution by this weight. And here then we have, we're sort of targeting a distribution that has the mean and covariance of the common distribution. So we can calculate what those should be, and now we've adjusted the likelihood ratio to go ahead and be sampled from, as if these prior samples were from this distribution, and that gives us this cyan curve, which clearly has the same statistics, which we were interested in. So these are the two things, the sort of two updates we're thinking about playing around with for the flow variable themselves, right? If the flow is somehow leading to a nonlinear distribution, sort of what could we do what sort of important sampling could we do to better target that posterior distribution? So and that's, I think I'm not going to go on to the next problem since I already went over. So I'll end it there.
This approach that you showed in the Schiller proposal, like the couple kind of filter and the particle filter, remind me an approach which has been used for joint parameter and scale estimation by people who some of them are built hydrological models.
And hydrological models?
Well, it started with phase parameters. The idea is that as soon as you augmented the scale using the parameter, and automatically the problem became nonlinear, so what they need was to shift the
Okay, yeah.
They shift these two palettes and some of them they use the mean estimated by state part, and then the feedback is
Right.
estimate the parameter. They do the update on the parameter and they come back. And
Okay.
they remind me more or less the same what you're doing here, but here the novelty
Yeah,
comes
no,
by
I would
the fact
definitely
that-
like to see references to that.
Two separate filters. This one, the hybrid one, it is like a marginalized filter sound, and this particle filtering on the filter.
Right, effectively.
Yes, more marginalization.
But the whole point of observing y is a function of x, right? But y contains information about x.
Mm-hmm.
So you have augmented it, and then you put y as 0i, therefore it just between the drifter.
Mm-hmm.
So therefore y contains information for x. So therefore I should also update my weights, I believe, in the calculation. So you sort of decoupled them a little bit, I don't know. Just a step.
Yeah, so that's what we were thinking. That's why we're sort of positing this.
One
But
before you had is decoupling.
right, so here,
The whole point of the drifter is drifter contains another information for x.
so here, I mean, we looked at it both ways. So the drifter is updated. We keep the old weight on the flow. So if we update the weight that we've updated here on the drifter coordinates, if we update that weight on the flow and we apply this algorithm to a Gaussian linear model, we don't end up with the correct statistics. So, so for the Gaussian, but the Gaussian case, this is a simple toy example, but I showed this in the Gaussian case, right? This is the ensemble common update of the green, so just shifted with the old weights.
The whole purpose of collecting y is to estimate x.
Right? No, totally. I mean, so.
This is written y on the
So effectively, this is only the resampling step. Right? The rest of the time, we can just think about this as a particle filter. The resampling step, basically how we thought about this is some of these flows are doing a really good job at getting drifters to the, to clouds of drifters to the observations. And some of them aren't. Right? And so we need to do something to change the ones that aren't, which is where the common update does. So effectively, we're in some way sampling the common filter there. And if things are linear and Gaussian, we sample the common filter, then it's just a linear transformation, so it just holds on to its own weight. So for linear transformation, that's exactly what we'd expect. For nonlinear transformation, it wouldn't work. I mean, it doesn't work in the cartoon.